Something rare is about to happen in the sky. And if you know where to look, tonight may become unforgettable. 7 days from now, a shadow 8,260 kilometers long is going to come down out of the Arctic, cross the ice cap of Greenland, cross Iceland, clip the northwestern corner of Portugal, cut through northern Spain, and drown itself in the Mediterranean near Majorca. It will be moving the entire time at roughly 3,400 kilometers an hour, faster than the speed of sound. It has not touched mainland Europe in 27 years, and it has not touched mainland Spain in over a century. And if I asked most of you right now what is actually about to happen in that narrow strip of sky, you would tell me the sun is going to get covered up for a couple of minutes, the sky is going to get very dark, like an unusually dramatic sunset. That sounds so obviously true that nobody bothers to check it. You would be about as wrong as it is possible to be about a fact you already halfway know. I want to spend the next while on that one wrong idea, because it isn't a fringe belief. It isn't something you'd find on a conspiracy forum. It's something held by people who read popular science, people who already know perfectly well that the moon blocks the sun, people who could sketch you the orbital diagram from memory. The idea is this, that a partial eclipse and a total eclipse are the same event at different volumes. That if you stand somewhere and get 90% of the sun covered, you've had 90% of the experience. That totality is just the far end of a dial running from 0 to 100, the way a room gets a little darker each time you close another blind. That is not what's about to happen on August 12th. And the reason it isn't philosophical. It's a specific number. And the number is 1 in a million. Here's the arithmetic nobody does. The sun's visible surface, the photosphere, isn't just bright. It's bright in a way that swamps everything near it. The sun's outer atmosphere, the corona, the pale crown of plasma heated past 1,000,000 degrees that only becomes visible during totality, is roughly 1/1,000,000th as bright as that surface. Not 1/10th, not 1/100th, 1/1,000,000th. Which means that even if only 1,000th of the sun's disk is still exposed, a sliver so thin you'd need a solar filter to notice it's there at all, that sliver alone is still putting out 1,000 times more light than the entire corona combined. Your eye can't tell the difference between a sliver of the sun and the whole thing, because the sliver alone is already blinding. That's why, if you're standing at 99% coverage a few kilometers outside the path of totality next Wednesday, you'll notice the light get a little strange, a little metallic, maybe some odd double shadows. You will not see the corona. You will not see one single star. Functionally, full daylight continues, because your eye and the sky don't care about your intuitions about the number 99. They care about photons, and the photons don't run out until they run out completely. That's the first crack in the belief. The dial from 0 to 100 model is wrong because human vision and the daytime sky don't respond to sunlight the way a dimmer switch responds to a knob. They respond the way water responds to a stove. Nothing happens, nothing happens, nothing happens, and then, at one very specific point, everything happens at once. That point has a name. Second contact. The instant the last visible edge of the photosphere disappears behind the leading edge of the moon. Right before it, you get what's called Bailey's beads, named for the English astronomer Francis Baily, who first properly described them in 1836. The last few points of raw sunlight breaking through valleys on the lunar limb, so that for a second or two the eclipsed sun looks like a diamond ring, one bright point of light set on a thin, glowing circle. Then the last bead goes out, and in the time it takes you to inhale, the sky changes state. Here's something I want you to hold on to, because it's the seed of a bigger argument I'm coming back to. If totality really does switch on and off like that, an honest either/or, not a dial, then the strip of ground where it switches on should be tiny compared to the region that only gets a partial eclipse. And it is. On August 12th, the path where anyone gets full totality is only about 293 kilometers wide, even though the partial eclipse, the boring, ordinary daylight version, will be visible across a huge stretch of the northern hemisphere, from parts of North America across Europe into Western Asia. A continent's worth of people will glance up, see a bite taken out of the sun through a filter, and go back to what they were doing. A ribbon 293 kilometers wide will see something else entirely. Why does the width work out that way? That's a question about geometry, and the answer connects to one of the strangest coincidences in the solar system. I'll get to it. In May of 1919, two expeditions from the Royal Astronomical Society sailed to opposite sides of the Atlantic to test an idea Einstein had published 3 years earlier, that gravity bends the path of light, and that the sun, being massive, should visibly shift the apparent position of stars whose light grazed past its edge. One team, led by Arthur Eddington, set up on the island of Principe off West Africa. The other set up at Sobral in Brazil. Both sites were chosen for one reason. Both would see a total solar eclipse that day, and nothing less would do. You cannot photograph stars beside the sun in ordinary daylight. The sky itself is too bright, for the same 1 in a million reason we just walked through. You cannot do it during a partial eclipse either, no matter how deep the partial phase gets, because that last sliver of photosphere ruins the measurement exactly as thoroughly as an untouched sun would. It had to be total, or it wasn't happening at all. When the plates came back and the star positions were measured against prediction, the shift matched Einstein's number, not Newton's. That is one of the most consequential afternoons in the history of physics, and it existed only because totality is not a deeper shade of partial. It is the one state of the sky in which that measurement could be made. 51 years before Eddington's expedition, in August of 1868, two astronomers working independently made an even stranger discovery using the same 1 in a million window. Pierre Janssen, watching a total eclipse from India, and Norman Lockyer, examining sunlight back in England, both noticed a bright yellow spectral line that didn't match any known element on Earth. Janssen could only see it because, for the length of totality, the sun's outer atmosphere was briefly visible without the photosphere's glare drowning it out. Lockyer worked out that the line belonged to an element nobody had ever isolated, named it helium after Helios, the Greek sun god, and it would be another 27 years before anyone found a trace of helium anywhere on Earth trapped inside a uranium mineral called cleveite. The second most common element in the universe was discovered in the sky before it was discovered in the ground, and it was findable at all only because, for a few minutes, the sun's disk was completely gone rather than mostly gone. That's the same 1 in a million ratio, showing up in a totally different field half a century earlier. Spectroscopy instead of general relativity, the 1860s instead of the 1910s. Every time in history that totality has mattered to actual science rather than just a spectacle, it has mattered because it was complete, not because it was deep. A 99% eclipse would have told Janssen and Lockyer nothing. It would not have been 99% as useful. It would have been exactly as useless as no eclipse at all, because the photosphere does not care about your rounding. Now the geometry. Totality is narrow because the moon's shadow comes in two parts. A huge, soft outer cone, the penumbra, where the sun is only partly blocked, and a small, sharp inner cone, the umbra, where it's blocked completely. The umbra is small because the moon is small and far away relative to the sun, so its shadow narrows nearly to a point before it even reaches Earth's surface, which is exactly why total eclipses are rare and annular ones aren't. On August 12th, the tip of that cone barely reaches the ground at all, carving a path only 293 kilometers across, racing along the surface at that supersonic 3,400 kilometers an hour, because the shadow is a fixed cone hanging in space while the planet spins underneath it. Stand in the umbra, everything happens. Stand 50 kilometers outside it, nothing does, no matter how close 50 kilometers looks on a map of a continent. But here's a question geometry alone doesn't answer, and it's the one that actually keeps me up some nights. Why does the umbra reach the ground at all? The moon is about 400 times smaller across than the sun. It also happens to sit, on average, about 400 times closer. Cancel out the coincidence and the two disks come out almost exactly the same size in our sky, close enough that the moon can just barely blot out the sun's disk while leaving the corona peeking out around the edge. That is not a law of physics. Nothing requires it. It's a fact about where the moon happens to be right now, in the year 2026, 4.5 billion years into a solar system that owes us nothing. And it is not a stable fact. It's already changing. And I want to tell you by how much, because the number is going to surprise you. During the Apollo missions, astronauts left small mirrored panels on the lunar surface, retroreflectors, built to bounce a laser beam straight back the way it came. Observatories on Earth still fire pulses at those mirrors today, more than 50 years later. And time how long the light takes to return? About 2.5 seconds for the round trip. That measurement is precise to a matter of millimeters, over a distance of roughly 384,000 kilometers, and it has told us something the ancient world had no way to know. The moon is moving away from us. Not dramatically, about 3.8 centimeters a year, roughly the thickness of your thumb, but relentlessly, every single year, for as long as the moon has existed. The mechanism is tidal friction. The moon's gravity raises tidal bulges in Earth's oceans, and because Earth spins faster than the moon orbits, those bulges get dragged slightly ahead of where they'd sit at equilibrium. That misaligned bulge tugs back on the moon, trading angular momentum out of Earth's spin and into the moon's orbit. Earth's rotation slows. A day lengthens by about 1.7 milliseconds per century, which is part of why leap seconds exist at all. And the moon spirals very gradually outward, the same way a figure skater slows down by extending their arms. When the moon first formed, something like 4.5 billion years ago, almost certainly out of debris from a collision between the young Earth and a Mars-sized body, it sat somewhere between 20 and 30,000 kilometers away, close enough that it would have looked several times its current width, and would have swallowed the sun completely during any eclipse, corona and all, with no delicate diamond ring and no thin remaining crescent at any point. It's been receding ever since, at a rate that itself shifts as ocean basins rearrange and continents drift, which is part of why nobody can hand you a clean, confident number for what comes next. But run the recession forward at something like its current rate, and the moon's disk keeps shrinking in our sky, eclipse after eclipse, and at some point in the future, the closest approach the moon can make will no longer be enough to fully cover the sun at its largest. When that day comes, whoever or whatever is watching the sky will only ever see annular eclipses again, a thin ring of blazing photosphere around a lunar disk that's simply too small. No corona, no total darkness at midday, no diamond ring. Most careful estimates put that day somewhere around 600 million years from now, though the honest range runs from about 500 million to something over 1 billion. Depending on assumptions about how ocean geography and tidal drag behave on a planet, we can't fully model that far out. I'll be straight with you about something, because you deserve better than false confidence dressed up as precision. That 600 million year figure gets repeated everywhere. I've said versions of it myself, elsewhere, with more confidence than I'd earned. And it bothers me more than it probably should, because the number depends on assuming the moon's recession rate stays roughly steady, and we already know it hasn't stayed steady in the past. Fossil coral growth bands and ancient tidal rock layers suggest the moon receded faster at some points in Earth's deep history and slower at others, tracking changes in continental shape and ocean depth that we can only loosely reconstruct for the past and can't predict at all for the future. So when someone states, with a straight face, that total eclipses end in exactly 600 million years, they're rounding a genuine scientific uncertainty into a clean headline, and I'd rather give you the true shape of that uncertainty than a fake decimal point. The honest answer is, sometime between roughly 500 million and a bit over 1 billion years from now, the sky is going to lose something it can never get back, and the moment we're standing in right now, this month, this eclipse, is closer to the start of that window than most people assume, on a timeline that makes the whole of human history look like a rounding error. I don't say that to undercut anything else I'm telling you tonight. The brightness ratio, the umbra's width, the speed of the shadow, all of that is measured, solid, checkable by anyone with the right instrument. I say it because a real argument should be able to survive admitting which of its numbers are load-bearing and which are our best current guess, and this is one of the guesses. The threshold is real. The exact date on the calendar is not. People have been trying to get this right for a very long time, with far worse tools than we have. Babylonian astronomers, watching the sky for centuries and recording it on clay, noticed that eclipses repeat on a cycle of about 18 years, 11 days, and 8 hours. the Saros cycle. Long before anyone understood why, purely by keeping careful enough records across generations. According to Herodotus, writing generations after the fact, the philosopher Thales of Miletus predicted a solar eclipse that occurred in the middle of a battle between the Lydians and the Medes in 585 BC, and the sudden daytime darkness so unsettled both armies that they stopped fighting and negotiated peace on the spot. Historians treat the details of that story with some caution, given how long after the fact it was written down. But the underlying instinct is correct. No culture anywhere, at any point, received a total eclipse as merely a very dark afternoon. It was always filed under a different category of event entirely. One of the sky's rare, discrete, threshold-crossing acts. Not weather, not a matter of degree, but a break in the ordinary rules of the day that demanded to be anticipated exactly or not at all. Every culture that watched the sky carefully arrived, independently, at the same intuition the corona to photosphere brightness ratio proves mathematically. People figured out that totality is its own category of event with the naked eye, millennia before anyone could explain why. By 1715, astronomy had moved from noticing eclipse cycles after the fact to predicting eclipse geometry in advance, and Edmund Halley, the same Halley the comet is named for, used Newton's newly published laws of gravitation to calculate ahead of time the path a total eclipse would take across England on the 3rd of May that year. He printed a map, circulated it widely, and asked ordinary observers across the country to time, as precisely as they could, the moment the sun vanished and the moment it came back, wherever they happened to be standing. His prediction landed within about 4 minutes and a few dozen kilometers of the truth. Remarkable for the period, and also, by modern standards, sloppy enough that whole towns just outside his line turned out to be inside the real one, and the reverse. Compare that to next Wednesday, when astronomers can tell you, a full week ahead of time, that the point of maximum totality falls in open ocean 45 kilometers west of a specific Icelandic lighthouse, and that totality there lasts 2 minutes and 18 seconds, not 17, not 19. The distance from Halley's 4-minute, few dozen kilometer uncertainty to a modern prediction accurate to the second and to a few hundred meters is 3 centuries of getting exactly one thing right, treating the edge of the umbra as a hard boundary, not a fuzzy one. Every refinement in eclipse prediction since Halley has been, without anyone framing it this way, an argument against the dial model. If totality really did fade in gradually, the edge of its path would be soft and forgiving, a matter of approximately how covered you happen to be. It isn't. It's a line. You are either inside it or you are not. And the entire 300-year project of predicting eclipses has been the project of locating that line more exactly, because everyone doing the math already understood, long before anyone could explain why, that there was nothing gradual left to measure once you got close enough to it. So put the whole argument together. The reason a 99% partial eclipse gives you nothing like the experience of totality is that light doesn't work on a percentage basis once you're this close to a source this bright. The corona is 1,000,000 times fainter than the surface, so anything less than complete blockage still floods the sky. The reason the path where that complete blockage happens is only a couple hundred kilometers wide, on a planet whose circumference is 40,000 kilometers, is the narrow geometry of the umbral cone, a direct consequence of exactly how big the moon looks against exactly how big the sun looks. And the reason the moon looks anywhere near the size of the sun in the first place. The reason totality is possible at all, rather than every eclipse in Earth's history being either a total blackout with no corona or a permanent ring with no depth of shadow, is an accident of a receding orbit that is actively, measurably correcting itself out of existence, 3.8 centimeters at a time, whether anyone's watching or not. 3 separate facts, 3 separate scales. Human vision, planetary geometry, orbital mechanics across geological time. And every one of them says the same thing. There is no smooth continuum here anywhere. It's threshold stacked on threshold stacked on threshold, and the belief that any part of it is a matter of degree is wrong at every scale you check it on. Here's what that actually looks like on the ground, for the people who put themselves inside that 293-kilometer ribbon next Wednesday. The umbra makes landfall, first at a lighthouse called Stromness, in the remote Hornstrandir region of northwest Iceland at 1743 Universal Time, where totality lasts about a minute and 26 seconds. It sweeps south across the Snæfellsnes Peninsula, over Reykjavik, and off the Reykjanes Peninsula, with totality stretching to 2 minutes and 13 seconds at Latrbjarg, the westernmost point of the country. And out over open water, 45 kilometers offshore from there, totality peaks for this entire eclipse at 2 minutes and 18 seconds, the longest anyone anywhere gets. From there, the shadow crosses roughly 600 kilometers of open Atlantic in about 35 minutes, before making landfall again in northern Spain, near cities like Burgos, León, Valladolid, and Soria, where totality runs a minute and 42 to 45 seconds, low in the western sky, with the sun only about 10 degrees above the horizon, low enough that across much of Spain, ordinary sunset arrives before the partial phases have even finished. It's the first total solar eclipse to reach mainland Europe since 1999. If you happen to be one of the people standing in Reykjavik next Wednesday, the arithmetic gets almost unfair. The city last stood inside the path of a total eclipse on June 30th, 1954. Before that, the year 1433. It will not happen again until May 26th, 2245. Whatever 2 or 3 minutes you spend looking up at the sky next Wednesday, if you're standing in Iceland's capital, is very plausibly the only total eclipse your entire family line will experience within 2 centuries in either direction. And if none of this feels abstract to you, if you were one of the tens of millions of people who stood somewhere across Mexico, the United States, or Canada on April 8th, 2024, when totality's path ran from the Pacific coast to the Atlantic, then you already know, in your body, everything I've spent the last several minutes proving with numbers. You already know that a 94% partial eclipse, seen from a city just outside that path, looked in photographs almost identical to what people 100 kilometers closer to the centerline experienced. And you already know it was nothing alike. That gap between nearly identical photographs and completely different lived experiences is the whole argument, compressed into one afternoon 2 years ago. In the minutes before totality, if you're standing in the path, the quality of daylight starts looking wrong before it looks dark. Flatter, grayer, shadows unnaturally sharp-edged, the way light looks through a cheap pair of sunglasses. Birds tend to go quiet. Some species head for their nightly roosts on a clock that makes no sense to them. Temperatures drop measurably, sometimes several degrees, in the space of a few minutes, because you're standing in an actual moving shadow, not a cloud, not a dimmer setting. In the seconds before second contact, thin, wavering bands of shadow sometimes ripple across pale ground or walls. Shadow bands, caused by turbulence in the upper atmosphere, distorting the last sliver of sunlight, an effect nobody fully agrees on the details of even now. Then Bailey's beads. Then the diamond ring. Then the last bead goes out, and for up to 2 minutes and 18 seconds you can look directly at the sun with your bare eyes, because there is nothing left of it to hurt you. Only the corona, pearly and asymmetric, streaming out several solar diameters in whatever shape the sun's magnetic field happens to be wearing that particular week, and, depending on your sky, stars and planets visible in the middle of the afternoon. Then, on the far side, the sun reappears exactly the way it left, in reverse, and it's over, and the sky goes back to being merely daylight, as if none of it happened, except it takes your nervous system a while to agree. One practical note before we zoom out the rest of the way. Next Wednesday is not, mercifully, humanity's last chance at any of this for a while. It's actually the appetizer. A little less than a year later, on August 2nd, 2027, an even longer total eclipse sweeps back across Spain and down through North Africa and the Middle East, with totality lasting up to roughly 6.5 minutes in parts of Egypt, nearly 3 times what anyone gets next week, and close to the practical maximum totality can ever last anywhere on Earth. If you miss the 2026 eclipse, or weather ruins it for you, that's the one to put on a calendar with real intent, not a vague someday. But don't let the existence of a longer encore talk you out of the shorter show. 2 minutes and 18 seconds of something that will not exist in this exact geometric form for most of Earth's remaining future is not a consolation prize for a 6.5-minute one next year. It's its own complete, unrepeatable event, and treating it as a lesser preview is exactly the same dial-shaped mistake we've spent this whole time taking apart. As if 2 minutes of totality is some fraction of 6.5 minutes of totality, when in fact both of them cross the identical threshold, the identical 1 in a million line, and either one alone is worth more than every partial eclipse you will see for the rest of your life combined. Zoom out as far as this deserves to be zoomed out. The moon has existed for something like 4.5 billion years. Life of some kind has existed on Earth for roughly 4 billion of those. Complex, eye-having, sky-watching life is a much younger story, and a civilization capable of measuring any of this. Lunar laser ranging, eclipse geometry, the brightness ratio between a corona and a photosphere, has existed for well under 200 years. Total solar eclipses, meanwhile, have a total lifespan on this planet of somewhere on the order of 1 billion years, give or take the honest uncertainty I already admitted to. Do the fraction. The window during which the moon's disk happens to sit close enough to the sun's disk in apparent size for totality to exist at all is a sliver of Earth's history. And the window during which a species exists that can notice, measure, predict, and travel to go stand inside that sliver is smaller again by several more orders of magnitude. You are not just watching a rare event next Wednesday. You are one of a genuinely, measurably tiny number of observers, out of everyone who will ever live on this planet across the whole of its habitable future, who happens to exist during the calibrated, temporary, actively expiring geometric coincidence that makes this specific kind of sky event possible anywhere. Every civilization that comes after the moon's disk shrinks past that threshold. And there's a lot more future left on Earth than past, assuming nothing else ends things sooner. We'll only ever read about this the way we read about eclipses scratched onto Babylonian clay. They'll have the equations. They won't get the diamond ring. Put a finer point on the fraction, because a number this small deserves to be looked at directly rather than waved at. Earth is roughly 4.5 billion years old, the window during which total solar eclipses can occur at all. Bounded on one side by however long ago the moon's orbit widened enough to let a full corona show, and on the other by the 600 million year horizon we already discussed honestly, is, at the very outside, on the order of 1/10 of that history, and probably a good deal less once you stop rounding generously. Now shrink it again. The interval during which a species exists on this planet that can point a laser at a mirror an astronaut carried to the moon, measure the round trip to the millimeter, and calculate exactly where a 293-kilometer shadow will fall a week ahead of time, is somewhere under 200 years, out of 4.5 billion. That's a fraction with more zeros after the decimal point than most people are ever asked to actually hold in their head at once. And next Wednesday's eclipse is one single instance drawn from inside it. So when I hear someone describe next Wednesday as the sun getting covered up for a bit, like a dramatic sunset, I don't think they've just got the astronomy slightly wrong. I think they've made the same mistake people make about almost everything that actually matters. Assuming that because something looks continuous from a distance, coverage climbing from 1% toward 100 like a dial slowly turning, it must be continuous up close. It almost never is. Water doesn't get gradually more like steam as you heat it. It sits there being water, stubbornly, right up until one exact degree, and then it isn't water anymore. A pile of uranium doesn't get gradually more explosive as you stack more of it together. It sits there being inert, right up until one more atom pushes it past critical mass, and then it isn't inert anymore. And the sky above a lighthouse called Stromness, on the far edge of Iceland, is not going to get a little darker next Wednesday, and then a little darker than that, and then dark. For every second up to the last one, it's going to look like an ordinary, overexposed, entirely explainable afternoon. And then, for exactly 2 minutes and 18 seconds, in one instant with no ramp leading up to it, the sky is going to stop being what you've called the sky for your entire life and show you the thing that was always underneath it. And then it's going to end, just as abruptly, and go back to pretending none of it happened. There is no such thing as 99% of an eclipse. There is no such thing. if you look closely enough, at almost anything. There's what hasn't happened yet, and there's everything. And the gap between them is thinner and colder and far more temporary than anyone standing at 99% will ever be told.